Okay, here's going to be some alternating series test examples I promised you guys earlier to do. So let's take a look here. Here's a series. It's going to be alternating. -1 to the n, square root of n, 1 plus 2, square root of n. Now remember, we talked about this portion here. This is our alternating mechanism, right? So we're going to call that the alternating mechanism. And then our Bn portion is right here. And here's that Bn. So Bn here is what we're going to have to take a closer look at. And remember, the alternating series test requires two things. It requires that this is a decreasing sequence here. If we look at that, it's decreasing. The terms are decreasing. And the limit goes to 0. And so a big part of this test is to determine that this is in fact happening. So there's a couple of ways we can probably look at this. And I would say to you, maybe kind of consider what's happening with some of these terms. I would say, though, more importantly, look at the numerator. Let's change these colors here. My numerator is a term square root of n. Now the denominator in comparison to the numerator, right? I got 1 plus 2 over the square root of n. So if you could notice that the denominator is actually larger, it's bigger. And this is smaller. And sometimes you can argue and say, well, the square root of n is less than or equal to 1 plus 2 square root of n for all n. And that's true. So you have the numerator over the denominator, smaller over larger. And so what's happening is the denominator is getting bigger much faster than the numerator. And so as n goes on, or we should say for every term, you're going to have a decreasing situation because of this relationship. This is decreasing. So this is one way we can consider that it's decreasing. Another way we can consider this is to look at this as a function and say, okay, I have the square root of x here, 1 plus 2 over the square root of x, and use calculus to show that that derivative is less than 0 for values of x. And so, that's kind of one way we can look at this situation, but I choose to see it the way I originally described it to you, that the numerator is smaller than the denominator, and that ratio, because of that, is a decreasing sort of situation. Now, you can prove it's decreasing, like I said, only by looking at calculus or looking at the definition of a decreasing, sequence, and that is looking at the relationship here. Bn plus 1, the next term in Bn, what's going on there? Bn versus Bn plus 1, and then that's going to be, if you show that this goes the other way, that this is decreasing. So you can prove it looking at this. Anyway, we have a decreasing term. So if we look at the limit here, this is a calculus 1 kind of question. And we're going to divide by the variable with the highest power in the denominator, square root of n. So this is going to be the square root of n, square root of n, square root of n. So we get the limit here of 1 over 1 plus, that's 1 over the square root of n plus 2 here. So let's be careful. And okay, so let's see where this limit goes, and looks like this portion here is going to go to 0. So we end up with this limit being 1 over 0 plus 2, or we can say this is 1/2. And this is not equal to 0. Now, by the alternating series test, this doesn't mean anything. Because remember, if you have two things, if it's decreasing, it is. If that limit equals 0 for Bn, both of these have to happen. Right? If you have this, then we say that this converges by the alternating series test. All right, here we go. This limit is 1/2 and it's not 0. Okay. Nevertheless, this is good information. Okay, I'm going to put this happy face here. Because what this then means for us is that the limit of An, if we include the alternating mechanism, and the square root of n here, over 1 plus the square root of n, we know that this limit, as n goes to infinity, is plus or minus 1/2. This information is important for us. Plus or minus 1/2. This limit does not exist. And so what we say here is by the test for divergence, this is a divergent series. We have divergence. And this is how we use this. So this diverges by the alternating series test. Okay. Another example. Now, here's a test that involves factorial that was requested today. So, again, let's remember here, this is the alternating component, the alternating mechanism. We have this portion here, Bn. So that Bn here is n to the n over n factorial. And this is true for all n. Right? This is defined, I should say, for all n. Okay, so we had this request. Let's do some with factorials. Here it is. And let's see what this gives us. Here's what I want to say. I want you guys to note what this is here. That n over n factorial, by definition, is n times n times n times n. That's my numerator. And we have n of those things. We have n factorial, which by definition is n times n minus 1, n minus 2, times 2 times 1. So I know up here we have n of these. So what I'm going to do now is this. I'm going to take a look at the details of this. So notice we have n over n times n over n minus 1, n over n minus 2, n over n minus 3, all the way down to n over 2 times n over 1. And I can point out to you that we have cancellation here. And so if we're looking at this in terms of the product of every term, I have n here, n minus 1, n minus 2, n minus 3, n over 2, n over 1. And then I'm going to say, take a closer look at each one of these terms here. So I want you guys to do another note within a note that when you divide here, this n minus 1 with n, you take n over n, which is 1. And then 1 times n minus 1, subtract, you have 1. I'm left with this remainder here. So I have this quotient, remainder, doing my division. So this first term that we're looking at, I can replace with 1 over n minus 1. And in fact, I could do this for every one of these terms here. So that first portion is 1 plus 1 over n minus 1. And you say, well, what about the next one? Well, try that out. N minus 2 over n. We take these two n's and divide, and we get 1. We get n minus 2. We subtract. So this is going to be 1 plus 2 over n minus 2 when I write this as a mixed number, quotient, remainder, divider. And we'll get 1 plus 3 over n minus 3. And then we got to multiply all of these terms down to n over 2 times just n, because n divided by 1, if we see how this ends, this is just n. So I'm looking at the details of this. And what starts to show here is as a pattern, remember what you're seeing here. On the left side, we have n over n factorial is exactly what we just see here on the right. Now, every one of these terms, this term here, they're bigger than 1. Let's go back. Every one of these terms are bigger than 1. And so what we're showing here is that this is going to be greater than or equal to the last term, n. So this is n. So this is greater than or equal to n. And so if you take the limit now of, well, in some ways you have, one thing here, that since n is less than or equal to n over n for n factorial, the limit of n is less than the limit here of n over n to the n factorial. So if n gets big on this portion right here, this is going to infinity. So if the smaller sequence goes to infinity, you're going to have that larger sequence go to infinity. And so whether this is an increasing or decreasing sort of sequence, it doesn't really matter. We're looking at the whole thing together now, not as Bn, but we can look at the whole thing here as An, this whole sequence. And what we know is whenever that portion here goes to a value, right, or it goes to infinity, here's what this means. That the limit of An, which is the limit of -1 to the n factorial over, or n to the nth power over n factorial. Let's double check that that's the real question. Yeah. This limit is plus or minus infinity. Because the alternating mechanism, if this portion here goes to infinity, that we just found, the alternating mechanism here will make this go to plus or minus infinity, which really means that the limit does not exist. And if the limit does not exist of an, then here's what we know. This diverges by the test for divergence. So, you know, this really is something, even though the terms alternate, we're going to say that here's our conclusion. Diverges by the test for divergence. And that's what we're looking for. Here's our justification. So here's an example, and it's kind of interesting. Anyway. Okay. So they had a little bit of algebra here. So that's an interesting idea. Now, let's go to, I think I kind of lost my bearings here. Let's try another one here. Series 1 to infinity, negative 1 to the n minus 1, e to the 1 over n over n. Again, here's the alternating mechanism. Here's that b to the n. So, bn, e to the 1 over n over n. And if you said, well, what does this kind of look like for us? Is this decreasing, right? Well, if we look at the terms, b1 is really e over 1, and that's e. b2 is e to the 1/2 over 2. b3, e to the 1/3 over 3. We got to see, may not be so easy for us to see if this is increasing or decreasing. Right? So one thing we can look at is to consider this function f of x, e to the 1 over x over x. So let's kind of do that. I think let's try to see by taking the derivative, the values of x for this function here. Let's do sign analysis, find where this is increasing, or more importantly, where it's decreasing. So some examples will have you do something like this. Now I need the derivative of 1 over x minus 1 over x squared. Okay. X e to the 1 over x minus 1 over x squared minus e over 1 over x squared minus e to the 1 over x, and I think that's going to be over x. We'll write it that way. Minus e to the 1 over x. Over x squared. So we're going to factor out a e minus e to the 1 over x. I have 1 over x plus 1, everything over x squared. Doing some algebra. Minus e 1 over x plus 1 over x divided by x squared, which is minus e to the 1 over x plus 1 over x to the 3rd power. So you guys can double check to see if we make any mistakes on this thing here. Let's go back. Yeah, double checking everything kind of quickly there. Now remember, we're supposed to do sign analysis on this. You want to know where this particular rational derivative, equals 0, right? So f prime x is 0 when that minus, we'll take that minus sign, e to the 1 over x plus 1 is 0. And that means two things. Minus e to the 1 over x is 0, and this never happens. And x plus 1 equals 0 happens when x is negative 1. Okay. The second part of this is, where is this actually undefined? We want to highlight that. Well, that's when x cubed is 0. So we have that, you can say does not exist, the derivative. And that happens when x is 0 here, because it's really x cubed is 0 or x is 0. So if you had to do sign analysis on that first derivative, I would say at 0 and then at negative 1, undefined. I'm sorry, it's not that, it's 0. And then at 0, our derivative does not exist. And this is on f prime. So notice something here. I'm going to test this at 1. So I have 3 regions that I'm supposed to test by sign analysis. And when I plug in 1 here, here's what you end up getting. 1, 1, and 1, and 1. We get f prime of 1 is minus e times 2 over 1, or just simply minus 2e, which is going to be negative. So I found this portion here is negative at 1. So that means in this quadrant, we got negative values. We have a decreasing situation. Now, I don't really care about the other particular regions to test, because if our domain here is natural numbers, that only applies to region 3 here. So this is decreasing, and so we say f prime x is less than 0 for x greater than 0, but we're dealing with a sequence here. So f prime n, or I should say, let's go back and say that the sequence an, which is fn, or in fact, I think this might be the bn, right? Yeah. bn, which is our sequence, and you say, where is it? Way up here. This is decreasing. Okay, so we know for certain this was a little bit tougher to kind of reason to determine if it was decreasing. I mean, we could look at the numerical values, I guess, and you can kind of see that it's decreasing as well, right? You start with E and so on. So we could have looked at these values here. But I did this all without a calculator anyway. So we're using calculus since that's what this course is. It's decreasing. We need to know the limit now. So we know it's decreasing. So let's look at the limit of e to the 1 over n as n gets big and see if we can determine what this goes to. Now, here's what I want to say. As n gets big, we have 1 over n goes to 0, which is e to the 1 over n, goes to e to the 0, which is 1. So my numerator goes to 1 as the denominator gets big and goes to n. So this means denominator gets big and goes to infinity. E to the 1 over n will go to 0 because the top portion here, this top portion goes to 1 and this gets big arbitrarily. 1 over something very big goes to 0. So we show that this limit is 0. And more importantly, what this means is we have convergence here. So this converges by the alternating series test. By AST. And that's what we have here. And something very similar happens, like if I said to you, what happens if they gave you a series that looks like this, something extremely similar. 1 to infinity, negative 1 to the n minus 1, natural log n over n. Again, we have the alternating mechanism here. And we're going to let this be our b to the bn. So we get ln n over n. So is this increasing or decreasing? I'm going to consider the function natural log x over x. And we're going to find where that derivative is less than 0, because that means we have a decreasing for what x. So if I differentiate again using quotient rule, x squared x, derivative of natural log x minus natural log x, let's see what we get. X times 1 over x minus natural log x over x squared. We get 1 minus natural log x over x squared for that derivative. And so you say, where does this equal 0, right? We're doing sign analysis on this. So the derivative is 0 when 1 minus the natural log x is 0, or the natural log x is 1, which means x is e. That's where I have 0 for a derivative. Now, the derivative does not exist, so we focus first on this numerator being 0, right? And that gives us the value of x. The denominator being 0 now, that means x squared is 0. Well, that means x has to be 0 here too. So we get x is 0. I get x is e. When x is 0, the derivative does not exist. When x is e, the derivative is 0. So that gives me 3 quadrants again. Quadrant 1, 2, and 3. Now, here's something that's happening. We need some test points. Now, e is approximately 2.718, so I can test the value 1, and I can test the value 3. So I can plug those into the derivative, because that's what we're doing sign analysis on, this derivative. So when it's 1, if we plug in 1 now, let's erase these things. I get 1 minus the natural log of 1. This portion is 0, and that's positive. And don't forget that's over 1. So it's really over 1 squared. So this is 1. It's positive. If I test 3 now, and I plug in 3 here, and this is now 3 squared. So I get 1 minus the natural log of 3 over 9. Now, 1 minus the natural log of 3, that number is negative. So this portion will be negative here. What that means is our function f is increasing on the interval 0 to e, and it is decreasing from e to infinity. So one thing you could do here is you can consider the following, right? Because this is now, remember, if you look at this function here as having a domain of natural numbers, which is what we're looking at, and it's not an again, it's bn. And that's, oh, what do we have here? What was that function again? Natural log. Okay. ln n over n. So my Bn is natural log n over n. It's decreasing really starting at n is 3 and 4 forever. So when n is 1 and 2, it's actually increasing. We're looking at this. This is n is 1. Here would be n is 2. So how we can really do this, if we wanted to be technically exact with the theorem for alternating series test, is I'm going to write this way. I'm going to say we have, this series, we're going to look at as plug in 1. So we're going to have the following. We're going to have negative 1 to the 1, natural log of 1 over 1 plus negative 1 squared, natural log 2 over 2 plus this starting at 3. Negative 1 cubed, natural log n over n. So I have two finite values here. Let's see what this really is. This is 0. So this first term is really negative 1 plus the natural log of 2 over 2 plus this series here starting at 3. So we're going to have to talk about the convergence or divergence of this series here. And if this series is a finite value, well, we just simply add, two other finite values together and the sum is finite. So we have convergence. Or if it diverges, that's infinity. Well, infinity plus some finite values is still infinity. So this really is what we test. And the answer for this, in terms of convergence or divergence, really applies to the question where you actually start at 1 here. So, I mean, there's some detail there. So I want to show you guys some of these details. And then now, and that's not 3, but that's n. It starts at 3. And I want to show you some of these nice details. So we know it's decreasing, right? We just shown that it was decreasing because we did the calculus for this. What's the limit now? Okay, and we say, okay, the limit of Bn is the limit of natural log n over n. N gets big. We get infinity over infinity. Well, by L'Hopital's rule, and we can't use L'Hopital's rule for the domain being natural numbers, we're really going to look at the limit of natural log x over x as x gets big is the limit as x gets big, derivative of the natural log x over derivative of x. 1 over x. The limit of 1 over x, and that is 0. And we know this by, we just used L'Hopital's rule here. Okay, so what that means is the limit as n gets big, natural log n over n is also 0. So it satisfies the criteria here of the alternating series test. So this here, we say, I guess I'll put it in red, converges by the alternating series test. This is finite. It's a finite value. If I add two other finite values to a finite value, well, the sum is finite. So this thing converges. It's finite. Right? Because remember what that meant? The sum is a finite value. We could write it this way. So we showed that even starting with 1, even though it was increasing at 1 and 2, it started decreasing at, starting at E, technically, or starting at the third term. So we can do do that. That's perfectly fine. Sorry. Okay. Just looking at my notes with some interesting examples. And it looks like this is another factorial question. So this is one where people may appreciate because it has factorial. Although, let's really look at the details here. Let's get our computer back. And I want to say something. This is kind of special in a way. You're going to have to consider, is that an alternating mechanism? Right? Is that alternating? Not sure. Let's take a look at this one. If we look at terms, I want you guys to note that, if n is 1, you get sine of pi over 2. Sine of 90 degrees, ladies and gentlemen, that's 0 when n is 2. Sine of, we get 2 pi over 2, which is sine of pi. Well, that value is negative 1. Yeah, let's double check. When n is 3, we get sine of 3 pi over 2, which is sine of 270 degrees. So we got pi, 2 pi, 3 pi. Right? You're gonna, if you want, take a look at the sine curve. I'm sorry. We got some things to consider. Let's go back. Sine of pi over 2. This is positive 1, not 0. Good. Right? So let's look at these terms. It's always good to draw the picture. Okay? So that's 1. And then you say, what about sine of pi? Well, that one's 0. Yeah, now it makes sense here. And then sine of 3 pi over 2, and this is negative 1. And if we say sine of 4 pi over 2, which is sine of 2 pi, which is 0. So we have positive 1, we got 0, we got negative 1, we got 0. If we continue with the pattern, the alternating part only happens when n is 1 and n is 3. Because if I come back and say, let's let n be 5 now, we get sine of 5 pi over 2 is positive 1. So n is 1, n is 3, n is 5. We got 1, negative 1, positive 1. This is where we start to alternate. And these are odd values, right? 1, 3, and 5. For the even values over here, we don't care about these because that's 0. So we don't care about the even values, only the odd values. So we do have an alternating mechanism, but it's not cosine n pi. This is a little bit deeper, a little bit different. So it's helpful for us to draw this picture so we don't make mistakes. So this is what I urge you guys always to do. And like I said, if I didn't do it, I'd make a mistake. So I'm going to rewrite this here. I'm going to rewrite it in such a way that I want to represent only the odd terms. Now, how you can describe being odd, by the way, we can say 2k plus 1 or 2k minus 1. This is how we describe in general odd numbers. This is even the definition. If you guys didn't know, that's a definition really of an odd number. So take your pick, positive 1 or negative 1. So in this example, what I think I'll do is I'm going to use the index k. And I'm going to say here, k starts at 1 here. Ends at infinity. And I'm going to replace now this portion down here, this n factorial. I'm going to replace it with the definition of an odd number, because only the other numbers, if I didn't, will be 0. Half of them will be 0. So I'm going to use 2k plus 1. So this will be now 2k plus 1, and then that'll be factorial. Now, what's the numerator? That's negative 1 to the k power. So you say, why did you choose k for that one? Because when k is, well, let's see. When k is 1, we need it to be positive 1. So let's say k plus 1 then. And double check. If I plug in k being 1, I'll get 2. And yes, that term is now positive for the first term. And then k being 1, I actually have to change that. That has to be minus 1 if I start with k being 1. Okay, so this is really what's going to happen. So it has to be a minus 1, not the plus 1. I can change it. If I want to use plus 1, I have to start here now with k being 0. Maybe I want to do that one instead. And if k is 0, this is just k. So maybe I can make it simpler by doing that. The point is, this is what my terms will look like. This is what I want to see, whether it converges or whether it diverges. So we want to look at one with factorial here. And this is the request we've been getting. So I want to look at this very special situation where you have that n pi over 2. That's kind of a semi-alternating mechanism. Okay, semi. Alrighty, here we go. Now we know two things. This is my alternating mechanism. And we'll call it that. What that means is my bk is 1 over 2k plus 1 factorial. Yeah, let's double check to see if we're okay. Yeah, we're fine. Okay. Now, this term is decreasing, and we can see that it's decreasing easily because my denominator is getting bigger. My numerator stays constant. So if my numerator is constant and the denominator gets bigger, that ratio gets smaller. So it's decreasing. The limit, k goes to infinity, 1 over 2k plus 1 factorial. Now, people want to know what that limit is. So let me show you something kind of interesting. You know, the definition of factorial. I'm going to put 2k plus 1. And then down here, 1 less is 2k. And 1 less is 2k minus 1. That goes down to 2 times 1. Okay, so I'm writing down here what this means to be 2k plus 1 factorial. These are for the people that want to see those factorials. And this is still the limit as k gets big. What you can do is write the limit as k gets big. 1 over 2k plus 1 times the limit k gets big, 1 over 2k, and you do that forever now, right? 2k minus 1 all the way down to the limits of your constants. Limit of 2, limit of 1. Here's my point. These are going to 0. So this limit equals all those products go to 0. And that's true for all k. So we showed, or we know, that this is decreasing and that the limit here is 0. And so here's what this really means. by the alternating series test, we have convergence. And that's dealing with a factorial, like the request we had this morning. So anyway, we got some factorials there. Good. All right, let's look at some more here. Here's another interesting example. One to infinity, -1 to the n, cosine pi over n. So we identify that this has an alternating mechanism up here. This portion here, cosine pi over n, this here is your bn. So we get cosine pi over n. And I'm going to say, to point out to you, is this increasing or decreasing? Right? What's happening with those terms? Well, I want to note a few things that you're really looking at for the first term, cosine pi, and you're looking at cosine pi over 2, cosine pi over 3, and cosine pi over 4. You're going forever. So what you really consider here, how I see this when I'm trying to figure this out, is it increasing, is it decreasing? What's happening with the terms of the sequence? I'm going to look at cosine. Now cosine looks like this. If I can draw it. Something like that. Pi over 2, +1, -1. So I'm really focusing on this interval here. So for the first term, cosine pi is down here. And then we have cosine pi over 2. And then it gets pi over 3 and so on. So we're going from -1 to +1. So this is actually increasing. Right here, n is 1. Here, n is 2. We went from -1 to 0. And then n is 3, n is 4, and so on. So this is actually increasing. So you can't use the alternating series test. But then you might say, well, why are they giving it to us in this section? Because this section is also about the divergence test. So I'm going to say, consider the whole thing. AN. This whole thing is AN. So we're going to use, because we know that we can't use the alternating series test, we're going to take the limit now of AN, which is that limit of the original question, -1 to the n, cosine pi over n. And we need to know, let's write everything down. N's going to infinity. Here's what we need to know. As n gets big, what happens to pi over n? Pi over n goes to 0, which means cosine pi over n goes to cosine of 0, which equals 1. And that means -1 to the n, cosine pi over n goes to plus or minus 1. So this limit is plus or minus 1. And you can't go to two locations. We say that limit does not exist. So since that limit does not exist, what's going on here is that this diverges by the test for divergence. Test for divergence. This diverges. And so, ladies and gentlemen, diverges. More importantly, what's the reason? What's the justification? Test for divergence. So notice we can't even apply the alternating series test because it's an increasing, that portion for Bn is actually increasing. It's not decreasing. So, I mean, that's how you want to consider these. Anyway, let's do one more. One last one, because we have an interesting question. We'll do one more for the road. One over negative n over 3 to the n. Okay. Just getting these notes together. And at first glance, you take a look at this question, and at first glance, I'm going to do a little algebra. That's negative 1 to the n over 3 to the nth power. That's what this whole thing is. And that's what we're looking at. 1 to infinity. Okay. Now, alternating mechanism. So that means our Bn looks like this. So Bn will be n over 3 to the n. And this is decreasing. Right? If you look at your terms, you might say, okay, my first term will be 1 over 3. The second term is going to be 2 over 3 squared. And then 3 over 3 cubed. And then 4 over 3 to the fourth. And that goes on forever. So I get 1/3, 4/9, 1. And then we get this 4 over thirds, which is bigger than 1, by the way, raised to the first power. So we have a... Oh, I take it back. We have what? This is increasing. These terms are increasing, ladies and gentlemen. We can't use the alternating series test. This is increasing. Oh, I wonder why they gave it to us. Well, because this isn't just about the alternating series test. It's really also by the test for divergence. They're trying to link these two together for you guys. So this is increasing. It's not decreasing, right? You went from 1/3 to 4/9 to 1 to more than 1 to the fourth power, and that's getting bigger forever. This is increasing, these terms. Okay, we know it's increasing, so don't even try to find the limit hoping that it equals 0. You're going to find the limit anyway. So the limit here, now we're going to look at the whole thing. This is going to be, the whole thing is an. Because we can't even use the alternating series test. We're going to have to try the test for divergence, which means the limit of an. The limit, n gets big, negative 1 to the n to the n over, it's n over 3. All right, so here's what this means. As n gets big, you're going to have n over 3. N over 3 gets big, ladies and gentlemen, right? Which means n over 3 to the nth power gets big. So negative 1 to the n over 3 to the nth power goes to plus or minus infinity when we include the alternating mechanism here. So this is plus or minus infinity, which means does not exist. You can't go to 2 concepts. It's going to 2. It's alternating between positive infinity and negative infinity. That limit does not exist. And so what we say here, here's our conclusion. This diverges. Now put it here. Diverges by the test for divergence. So there you go, ladies and gentlemen. Diverges by the test for divergence. So here is the series of examples that I promised I'd give you guys today, some extra examples. I hope you guys enjoyed it. I'll upload it now and take a look at this. This is really good stuff, okay? So not every term here that you get for BN is decreasing. Some of it are increasing because they really want you to use the test for divergence. All right, good to go.